All right, happy snow day, everybody. I miss seeing you guys, and I hope everybody's having a great day. I hope that you've been able to go out and actually play in the snow and have fun in it, and not just look at it from inside, the way I have. But anyway, I'm sorry that I have to give you this lecture via video, but we have to do what we have to do, so let's get on with it. Um, we've been studying how heat flow affects one and only one object at a time. So we've been identifying whatever it is that we want to look at as our system, quote unquote, and we've been considering everything else, the surroundings. And we've been using this variable Q to define the heat that's going on within that particular system. And we've said in a very technical sense that whenever one thing loses energy, the other thing gains heat energy. So our thermal energy is being transferred from our systems to our surroundings or from our surroundings to the system, depending on what is particularly happening in that instance. But a system is whatever we've defined it to be. It's that ice cube I've taken out of my refrigerator and put on the kitchen table, and then watched as the energy, it absorbs the energy from the room around it and melts into a puddle of water. So that's an example of a system and energy transfer to surroundings and vice versa. Okay, so that's what we've been studying so far. But we're in chemistry, aren't we? And we want to understand how heat flow happens in chemical reactions. So that's what we're working on in this lecture. So let's start off by defining a couple terms. Number one, I want you to know the word enthalpy. The word enthalpy, I think, is one of the weirder words in chemistry. It sounds to me like a disease. Poor guy, he has a bad case of enthalpy, but it's actually the heat content of a system. So we say, how much enthalpy does this system have? And you know, we're talking about heat content. All right. Okay. So the other thing I want you to think about is heat flow. So we had flow from a system to surrounding or vice versa. We call it delta H, but we're using H here because now we're talking about more complex situations where we've got heat flow happening as the result of a chemical equation, a chemical reaction. And you know that when you've got a chemical reaction, you have one, two, three, or even more chemicals that are combining to do something, either to gain heat or to release heat into the environment. So we call that change in heat flow delta H in these reactions. And remember, too, what we've already sort of talked about, and that is that reactions are either exothermic or endothermic. Now, you may say, wait a minute, I've been in chemistry a while now. We've done a bunch of experiments. I have never felt any heat either being lost or gained as the result of any of the reactions that I've done. That could very well be. Sometimes the heat that is released or gained is infinitesimally small, and we're dealing with very small quantities of the product, and so it's not really noticeable. Theoretically, it's possible you could have a reaction that doesn't have any heat gain or heat loss, but in general, uh, just about every reaction does have heat gain or heat loss. It just might be very, very small. Or in some cases, it could be extremely large. It just depends on what's reacting and what quantities we're talking about. Okay, so you already know the terms exothermic and endothermic. So when we release heat in a reaction, it's called an exothermic reaction. When we gain heat in reaction, heat is absorbed from the surroundings. We say that that is an endothermic reaction. And it makes sense that the reactants have either greater heat energy than the products in an exothermic reaction, or they can have less if it's an endothermic reaction. Okay? And we annotate the heat flow that takes place in these reactions either as negative delta H when heat is released in an exothermic reaction, or positive delta H if heat is absorbed in an endothermic reaction. So, and this makes sense, doesn't it? Because what I'm looking at is what's the end result. In an exothermic, heat has been lost, and therefore negative makes sense. Endothermic heat's been gained, positive makes sense. All right? So, we know it's gained or lost. The next question probably on your mind is, holy cow, am I going to have to quantify this? Am I going to learn some formula to quantify it? And the answer is, of course you are. This is chemistry. So we are going to talk about how to do that. There are many ways. Some of them are very, very sophisticated. Thankfully, what we're going to learn about today is the very simplest way to do it. It involves math that you probably learned by fourth grade. So there's a lot of terms that'll fly around in this lesson, but know that the math that's involved is very, very simple math. Oh, and by the way, when I talk here about exothermic and endothermic reactions, and I've got a negative or a positive delta H, you're going to have to do calculations where your end result is either going to be a negative delta H or a positive delta H. And a question is likely to appear, is this an exothermic or endothermic reaction? So you're definitely going to want to know how these terms uh, are valued compared to exothermic and endothermic. All right. So, like I said, we're going to learn the very simplest method to compute the heat flow in a reaction, thankfully. And this method that we're learning only works at STP. Now, STP was a famous gas additive that was advertising constantly on TV when I was a kid. But I don't know if you guys are familiar with STP as an additive to your engine to make your car perform better or not. But STP in chemistry means standard temperature and pressure. Okay, standard temperature being basically room temperature. So 20 to 25 degrees centigrade is considered standard temperature. Standard pressure is 1 atmosphere. So these are conditions under which you and I normally operate and live in. And these are specific to this particular heat of formation that we're going to use. So every item, just like it had a standard specific heat, has a standard heat of formation that we use. And we annotate the standard heat of formation as delta H and then a little degree sign and then a subscript lowercase f. So this means standard heat of formation. And like I said, every substance has a certain value for its standard heat of formation that's identified as joules, in other words, the amount of energy per mole of the substance. Okay? So, the good news is when we do these in this class, we're going to provide you with two things that are really going to make this much more straightforward for you. Number one is we're going to give you a chemical equation. Okay? Number two, we're going to give you a chart. And a chart will show the standard heat of formation of each reactant and product that's involved in your chemical equation. So all you're going to need to do is construct the right calculation in order to figure out the standard heat of formation for each item and then go ahead and calculate um, how much heat flow you've had. So there is one exception. There is one type of thing that will not show up on the charts that we give you necessarily. We may throw it in there, but we're likely not to. And that is that any lone element, including the diatomic elements, will always have a standard heat of formation of 0. So let's say that I've given you a formula and I've given you your chart. but the reaction involved is a combustion reaction, all right? So you have some product, maybe it's methane, and it's combining with diatomic oxygen, O2. O2 may not show up on my chart, right? Because it's going to have a standard heat of formation of 0 because it's a lone element, and you're going to have to just know that. Okay, so what do we do? Well, step one in chemistry seems to always end up being balance the equation. So hopefully that's become second nature to you at this point. The second thing we do is we just populate our calculation. And what is our calculation? All that we do is we look up on our handy dandy table we've been given and we've said, what are the standard heat of formation of each of my products? And I'm going to add those together. Okay. Then we say, what are the standard heat of formation of my reactants? I'm going to add those together. And I subtract the sum of the standard heat of formation of my products. Well, I subtract the standard heat of formation of my reactants from the standard heat of formation of my products. So note here a couple things. Number one is my reactants. Remember, reactants are always over on the left side of the equation, right? When I give you a chemical equation. Um, and products are always on the right side. So we're doing a switcheroo here, aren't we? And we've always got our products added together minus our reactants that have been added together. Okay? So you can see simple math here, right? Addition. All we have to do is remember to do the switcheroo, look things up in the table. If it's an element, we know we need to just have a 0 for whatever that element is. And we've got things basically done. Now, there's one more thing that we have to know, and that is this is all based, as I said up here, on joules per mole. So if you have balanced your equation in step one and you see that something has a coefficient, then you've got to go in and say, okay, I had a coefficient of 2, for example, on this. So I need to take whatever my standard heat of formation is here and multiply it by 2. Maybe over here for this reactant, you had a coefficient of 3. You would need to multiply this standard heat of formation for that reactant by 3. Okay? So that's the only complexity that arises in this. And again, keep in mind that standard heat of formations are always just given to you in a table. They could be very large, they could be very small. They could be positive, they could be negative. Once you do the math, your answer will end up either being negative or positive, either one, because your reaction could be either exothermic and negative or endothermic and positive. Okay? And remember that when we look things up for our standard heat of formations, that values are given to us in joules per mole. And that's why we have to do this multiplication I talked about if we do have coefficients. So if I had 2 moles, I have to multiply by 2. Okay? The other thing to note that will rarely come into play, but might conceivably, is the standard heat of formation may vary based on a substance's state. And remember, state and phase are the same thing. So if you look at the table that we give you and you see that, for example, H2O is on the table as liquid and gas with different standard heats of formation, excuse me, then you've got to use the right one in your calculation. All right? Okay. Let's do some examples, shall we? All right. So here is my first example. This is obviously a very made up example, isn't it? But we're just going to first practice the structure of the problem for a second. Okay, so note I said that you would receive your a chemical equation, and you would receive a little chart that shows you for each reactant and product what the values are. And notice, you see exactly what I said. Some of these values are really small, some are very big, some are negative, some are positive. That's just the way the standard heats of formation are. Okay? The other thing you notice is your first step is always to balance the equation. And of course, since this was made up, I made up coefficients. So this looks like it's already been balanced, by golly, doesn't it? All right. So when we start to think about how do we write our computation, we remember that the first thing in my computation is going to be my products. So I've got to start off with AD or CB being the first part of my equation. So there it is, standard heat of formation of AD and standard heat of formation of CB. So here are my products. Note too that because I had this coefficient here on CB, I have to say 2 times standard heat of formation of CB. Okay? So, of course, by default, then, the last part of my computation is going to involve my reactants. So here's AB, AB, CD, CD. And I've got my coefficient of 2 here embedded in my equation to affect AB. All right, so I'm set up. Again, it's not bad math. So let's get going on this. Okay, so standard heat of formation of AD is negative 90. 2 times standard heat of formation of CB. CB is negative 2. Minus 2 times standard heat of formation of AB. AB is 35. Plus standard heat of formation of CD. CD, negative 10. Plus negative 10. All right. So now I'm all populated. And all I have to do, let me go back first and make sure, do I have my coefficients correct? 2 on CB, 2 on CB, there it is. 2 on AB, AB, there it is. All right, so I've got my coefficients correct. I've got my negative in the middle, and I'm adding within my products and within my reactants. So I should be good. So negative 90 plus negative 4 be negative 94. It's sort of weird to start off with a negative 94, isn't it? Minus 2 times 35 is 70. Okay, 70 minus 10 is 60. So negative 94 minus 60 equals negative 1. Whoops, I did that again. 154. Okay, and that's going to be joules. And I dropped my per mole, which is here, which is my negative heat of formation, because I've normalized the moles out of this. So I just say 154 joules. Okay, so very good. Got that one done. Let's move on to the next one. And this one, I did not set up my equation in advance. You can see I've got my handy dandy table going right there. So let's set this up. So remember, first I start off with my products, don't I? So I say 2 times, excuse me, N2O as a gas, dinitrogen monoxide as N2O gas, 81.6, 2 times 81.6, and that was positive 81.6, I see, plus 2H2O. I have to keep remembering, I've got to go back here for my products, don't I? Plus 2 times H2O is negative 241.8. negative 241.8. I'll put parentheses around this whole thing. Minus, there's my minus. So now I move over to my reactants. N2H4 is 50.6, and I have no uh, coefficients, so I just say 50.6 plus N2O4. Again, there's no coefficient here, is there? So N2O4 is a gas, 9.16, 9.16. Okay. I'm all set up. I just want to double check myself. So N2O is over here, H2O is here, N2H4 here, N2O4 here. All right, so I'm good to go. I didn't mess up, get things the wrong way. And I've got only two coefficients, and I've got them both inside. So I'm good on that. So now the next thing I do is I just do this math. Let's see. We'll see if I can do it in my head. All right, 2 times 81.6, 163.2 plus 2 times negative 241. So negative 483.6 minus 50.6 plus 9.16. Okay, 59.76. Okay, and I'm going to break out the calculator just to keep things moving. Okay, so 163.2 minus 483.6 minus 59.76 equals negative 380.16. Okay, so is this, oh, we forgot to look at the other one too. Is this endothermic or exothermic? It is negative, it is exothermic. The one we did up here, is this endothermic or exothermic? It is negative, it is exothermic. All right, let's do one more example just for fun. Let's see, it's not snowing anymore. Let's go and do this one. All right, so again, we've got to always remember that we start, oh, look at this. I've got a bunch of coefficients going on here, don't I? So I start with my products. So I'm going to start and say 5 times, and then CO2 gas, negative 393.5, negative 393.5, and then plus 6H2O. H2O is always big. This is going to be a ginormous number. Yeah, look at that. 6 times 241.8. Negative. Remember to get your negatives in if it's a negative number. Okay, there we have that. So I've got my products in here now, minus, let's look at the reactants. Okay, no coefficient, that's nice. C5H12 liquid, C5H12 liquid, negative 146.8. Okay, 8O2. Look at this. O2 is not on our table. Why? It's a lone element, right? So it has a value of 0. So I'm not even going to put it in my calculation. Now I can just double check. Okay, do I have my coefficients of 5, 5, 6, 6, 1, 1. Okay, very good. Now let's do the math. I'm definitely using my calculator on this one. 5 times negative 393.5 equals, that doesn't seem right. Let me do it again. I'm going to do it in reverse. Negative 393.5 times 5. There, that's better. Negative 1,967.5. Okay, plus, okay, negative 241.8 times 6 equals negative 1,450.8. Okay. And then minus minus would be plus 146.8. Okay. So now I'm going to go back and say 1967.5. Wait, did I do minus 1967.5 minus 1450.8 equals, okay, and then plus 146.8 equals negative 3,271.5 joules. All right. Now, that is a huge number. Is it exothermic or endothermic? It appears to be extremely exothermic. Does that make sense? Yes. And here's why. If you look at what it is, C5H12 is some sort of a hydrocarbon, right? It's getting oxidized. In other words, it's combusting and it's producing carbon dioxide and water. So this is a classic combustion reaction of a fairly heavy hydrocarbon. So yeah, it makes sense that it would be releasing a heck of a lot of energy out into the environment. So those are some examples of how to do standard heat of formation calculations.